Hi everybody, and welcome to another review session to help you prepare for your final exam in Calculus 3208 presented by CDLI. Today we're still in the trigonometry calculus business here, so we're going to look at specifically some applications of trig functions to related rates. Alright, let's get going on this. So we're going to try to understand the concept of the rate of change of an angle. That sounds like it's a little bit of a funny monster, so we'll look at that for a minute, and then we'll try solving some related rates problems involving the rate of change of an angle d theta over dt right here. Alright, so we move along. Okay, so we'll start off with a problem scenario and then we'll try and analyze it a little bit. So it says an 8-foot ladder is sliding down the wall. We've seen problems like this before, but we've never looked at the angles in terms of how they change. So it says the top end of the ladder is falling at a rate, so that's this point up here. That's falling at a rate of 0.5 feet per second, or a half a foot every second. So it's sliding fairly slowly, I would think. It says to determine the rate of change of the angle that the ladder makes with the floor. So we got to determine the rate of change of this angle down here at the time when the ladder is reaching 4 feet up the wall. So when this height right here is 4, we got to figure out what that stuff is. Alright, so let's look at the different quantities that are involved here. So really there's 4 different, well maybe 5 different components. We've got a changing triangle. So there are going to be 2 different angles, this one and the one on the bottom with the floor. There's going to be the height that the ladder reaches up the wall, we'll call that h here. And then there's the distance that the bottom of the ladder is from the wall, so that's going to be our x. There's also the length of the ladder, which is 8 feet. Now all of those things are changing with the exception of the length of the ladder itself, which is the constant 8 feet. Okay, so when we looked at situations like this before, we were able to analyze the related rates issues using Pythagorean theorem. Now, that's not going to work out here because that doesn't get the angles involved, and we're interested in finding out the rate of change of this angle down here. That is our theta. Okay, so let's look at, as the ladder falls, what's going to be the sign of each of these rates of change? So h is shrinking, so dh over dt is going to be a negative issue, and x is going to be growing as the ladder slides this way, so dx over dt is going to be a positive number. And then the theta that we're interested in, which is this one down the bottom, that's going to be a negative rate of change because as the ladder falls and this angle kind of gets squished this way a little bit. The other angle at the top would actually be increasing, but the one at the bottom is decreasing. So in terms of units, because we were told we were dealing with distance in feet and time in seconds, we have feet per second for both x and h. And we always measure, remember doing calculus, if it's at all possible, we stick with radian measure for our angles. So theta is going to be measured in radians, so d theta by dt will be radians per second. Alright? So you got to think now, not only are the lengths of the sides changing here, but the measures of the angles are going to be able to change as well. So that's where we get tricky with it. So here we go. This is the same example, but what we're going to do is we're going to analyze it now and put it together and see if we can solve the problem. So the 8-foot ladder is sliding down the wall. The top end of the ladder is falling at a rate of 0.5 feet per second. So let's write down the information that that gives us. That tells me that h is shrinking at this rate. So dh over dt is going to have to be negative 0.5. Okay, that's good. Determine the rate of change of the angle we make with the floor at a time when the ladder is reaching 4 feet up the wall. So we want to know what is d theta over dt when h is equal to 4. So there's only 2 primary variables we're concerned with here, height and theta, and then just our rate of change we're differentiating with respect to t. So let's find a relationship between h and theta, and we'll try to keep it as simple as possible. So there's a couple of the real simple trig ratios, sine, cosine, and tan. There's a couple of those we could use here. We could use the tan, and then we'd have h over x is going to be equal to tan theta. Or we could use the sine, and we'd have h over the length of the ladder equals the sine of theta. I'm going to go with the sine because this is way easier to deal with because that 8 is never going to change. So what we can say here then is that the sine of angle theta will be equal to h divided by 8. Okay, so if you don't like fractions, you could say 8 sine theta is equal to h, if that makes you feel a little bit better about it. So we want to relate their rates of change now. So let's go ahead and differentiate and see what comes out of this. So the left side, using implicit differentiation, is going to be 8 times the cosine of angle theta. But remember, everything is a function of time here. So we have to multiply by d theta by dt after we differentiate there. And that's going to be equal to, excuse me, the rate of change of h will be the h over dt. Okay, so if I want to find out d theta over dt, I need to know what my angle theta is, and I need to know what dh over dt is. But I don't know what theta is. All I know is at a time when h equals 4. So if h is equal to 4, though, I can figure out what theta is because we have this relationship. So if h equals 4, then sine theta will be equal to 4 over 8, which is 1/2. And so we're less than 90 degrees for all these angles, so we're restricted to be no bigger than pi over 2. So that means that theta would have to be equal to pi over 6. It's going to be our only possibility for sine to be equal to 1/2 there. Alrighty, so now we can put everything together. So our equation for our related rate here is going to become 8 times the cosine of pi over 6 times d theta over dt, the one that we want, is equal to dh over dt, which is negative 0.5. So how fast is our angle changing? Well, let's work some stuff out here. Cosine of pi over 6, I believe to be root 3 over 2. So this is 8 times root 3 over 2 times d theta by dt is negative 0.5. So I can simplify this over here and call it 4 root 3. So I've got negative 1/2 divided by 4 root 3. I don't have a lot of space, so forgive me for squeezing things in here. So my d theta over dt that I want is going to have to be, so I have negative 1/2 divided by 4 root 3. That's negative 1 over 8 root 3, like so. And if I rationalize that, I'm going to get root 3 over 24, but it's negative. And that's going to be in radians per second. Okay, so we got that in radians per second. Sorry about the space issues. Okay, so that's a funny one. If you wanted to get that as a decimal value, we could do that as well. So it's going to be negative, and we want the square root of 3 divided by 24. So that's about 0.07 radians per second, or 0.072 radians per second. So that angle is changing at about negative 0.072 radians per second. Radians are a unitless quantity, but we'll run with it for now. Okay. Another one. This one looks tricky. A radar antenna on a ship that is 4 kilometers from the shore revolves at 3 rotations every minute. That sounds pretty slow for a radar antenna, but we'll take it. How fast is the radar beam moving along the shoreline when it makes an angle of pi over 6 with the shore? Okay. So let's get some quantities on here. If the radar is spinning at 3 rotations per minute, that's telling us how fast this angle down here is changing. So we better give that one a name alpha. So this tells me that d alpha with respect to time, 3 rotations every minute is 3 times 2 pi, so that's going to be 6 pi radians per minute. So that's our angular velocity, if you will. So that's d theta over dt. Okay, now we know we have a right angle up here, and this side is always going to be 4 kilometers. So what we're looking at finding is how fast is the radar beam moving along the shoreline. So let's call the shoreline x. And then x is going to be expanding if we are moving in the direction that's noted here, the way I put that angle expanding. Then x is actually expanding because that radar beam, or where it touches the shore, is moving in that direction right there. Okay. So I guess what we're really interested in, to find out the rate at which this beam is moving along the shore, that's going to be the same as the rate at which x is expanding. So we're after dx over dt. That's our goal here. What's that going to be? All right. So it's probably going to be in kilometers per minute by the look of the units that we have. So we need to get a relationship now between x and alpha. So it looks like x is opposite angle alpha, and it looks to me like the 4 kilometer side that won't change is the adjacent. So I'm going to use a tan ratio here. So I'm going to say that tan of angle alpha is equal to x over 4 kilometers. All right, or if you don't like fractions, 4 tan alpha is equal to x. Righto. Now, I've got to figure all this stuff out when the shoreline, it makes an angle with pi over 6 at the shore. So I'm betting I'm not going to need to know the angle I have with the shoreline. I'm probably going to need to know this angle in terms of alpha. So let's take a derivative here and see what we get. So we're going to have 4 times tan theta, which is going to be 4 times secant squared, alpha. And that's going to be times d alpha over dt, because everything is implicit. You're talking related rates. And that's equal to dx over dt. Okay, and just as I suspected, we need to know d alpha over dt, which we have, but we also need to know what is the measure of angle alpha. So right now, all we know is that at the time in question, theta is actually equal to pi over 6. So we should know that theta and alpha, since this is a right triangle, will have to add up to 90 degrees, or pi over 2. So our pi over 6 is going to have to be subtracted from pi over 2 to give us our angle alpha. Okay? So alpha is going to be, let's see, that's 3 pi over 6 minus pi over 6. 2 pi over 6, or pi on 3. All right, so now let's figure it all out. Our dx over dt, the one that we want, is going to be 4 times the secant squared of alpha, which was pi over 3, like that, multiplied by the rate of change of alpha with respect to time. So that's 6 pi radians per minute. Okay, and so we got to plug all that together. So let's evaluate secant squared of pi over 3 first. Well, secant is the reciprocal of cosine. I'm just going to make myself a little room over here and work that out on the side. So let's see, secant of pi over 3. Well, we should know that cosine of pi over 3 is half. So secant of pi over 3 is going to be equal to 2. So if I square that, secant squared of pi over 3 is going to be equal to 4. So this is going to be actually 4 times 4 times 6 pi. So we have 16 times 6 pi. So that's, let's see, 60 and 36 is 96 pi, and that's going to be in kilometers per minute. So if you wanted to work that out as a decimal approximation, you could. 96 pi is going to be somewhere in the ballpark of 300-ish. Let's see exactly. 96 pi is about 301.6. So this is about 300, let's say, kilometers per minute. And that's how fast the radar beam looks like it's sliding across the shore. That seems like a ridiculously fast speed, but when you think about it, if you're 4 kilometers away, and as that thing spins around, it doesn't have to go very far to make a big change in where that light is. So radar stuff goes pretty fast anyway. Let's take a look at the next slide here. So the next one is the your turn question. So it says a lighthouse is on an island that is 1 mile from a stretch of straight shore. A spotlight from the beacon is moving at 5 meters per second when the light makes an angle of pi over 4 with the shore. Determine the speed of the rotation of the beacon. Okay, I'm just going to give you a little hint with this one before you get started. Or actually, rather than a hint, I just got very apologetic about this. A couple of quick little corrections. This should be miles per second, not meters per second, because that's pretty slow for a lighthouse beacon. And I actually wrote the wrong angle here again. Wow. I'm so glad you guys are so forgiving and you don't mind. That's supposed to be pi over 3. So the angle of the shore is pi over 3. Okay, so it sets up situationally very similar to what we had in the last question. So give that a whirl and see what you can come up with, okay? Let's take a look now. Let me show you the solution. So here's the solution for this stuff, and you can see the corrections are already put in here. So work through that, and hopefully you got the right answer. 3.75 radians per second. That's pretty fast. Okay, let's jump on to the summary of everything that we looked at in this session here. So stuff that we've looked at so far: to solve a related rates problem. Now, most of this is very similar to what we did before. Find the relationship between the variables. If it deals with triangles, however, a trig relationship may be necessary to use, which is what we saw. And often a secondary relationship can be used. We didn't have to use those with these. Usually the trig ones are a little bit simpler than that, but you never know. Differentiate implicitly with respect to time, and then determine any required unknown quantities. Fill it in, and evaluate. Hopefully that was useful for you, and hopefully you're catching on to all this stuff and that you're preparing very well for your final exam. So I wish you all the best of luck.